Hello, my name is Jie Sui. I'm a professor from Wuhan University of Technology, China. First of all, I would like to thank the conference organizing committee who invited me to join this event online. I regret that I'm not able to attend the conference in person due to the COVID-19 pandemic. I hope my following presentation of all recent work will be of interest to you. So the title of my talk is Mesoscopic Modeling of Porous Electrode. Here's the outline of my talk, including introduction of the methodology, then the macroscopic model that most people already know, and followed by the discussion of the talk about mesoscopic modeling, and finally some remarks will be made at the end. Now the background and the motivation about why porous electrode and why mesoscopic modeling. So first, let's look at some devices that have porous electrodes. Here is the proton exchange membrane fuel cell, which has a few porous components. So how it works is hydrogen enters the anode and the air flows into the cathode and generate water. The heart of the PMFC is the membrane electrode assembly, which has porous components including the gas diffusion layer, catalyst layer, and microporous layers. For lithium-ion battery, the negative and positive electrodes are composed of graphite or metal oxides. The separator is also porous, allowing lithium ion to go through. There are other electrochemical devices such as this one, a vanadium redox flow battery, which has carbon felt material as the electrodes. Vanadium ion flows through the pores, whereas electrons are conducted through the fibers. So all these porous electrodes have multiple functions. They provide the pathways for non-charged species and charged species within the electrode space, as well as serve as mechanical support. Some of them have electrochemical reactions and heat transfer taking place as well. And some of these transport processes are often coupled. We would like to get understanding into these processes, but oftentimes local quantitative measurements are difficult, such as temperature and concentration. Therefore, we refer to modeling and simulation of this porous electrode at the pore scale level, which will be discussed in the remaining part of this presentation. So next, we look further on the topic of mesoscopic modeling, which you hear terms such as pore scale model (PSM), lattice Boltzmann method (LBM), and finite element analysis (FEA). So here is the flowchart of the workflow of a multi-scale approach. First, we start with reconstructing the materials using either images obtained from advanced microscopy such as X-ray, CT, or so-called fifth SEM, depending on the length scale involved. We can also reconstruct the structure using numericals based on observation from the material. So with such solid model, we proceed to perform numerical simulation on the pore-scale model using either commercial software or in-house codes. So the main purpose of this pore-scale simulation is to obtain the effective transport properties of the material, which will be used in the following macroscopic CFD models. So with experimental validation on the macroscopic models, we have then developed simulation tools for material design and screening, which can help component or system design. The basic idea of mesoscopic modeling is to obtain the effective transport properties of a porous medium, such as what's shown on the right image, For the derivation of a mesoscopic model, I would like to refer you to check out our recent review paper. For reconstruction and meshing, the first step is to reconstruct the microstructure. To do this, we could use images from all sorts of advanced microscopy techniques, such as the FIB-SEM and XCT. We can also simply reconstruct the structure numerically based on observation from microscope images. After this, we then convert these 3D images information to solid models and mesh these models according to the format of the software used for analysis. Some popular software include ImageJ and Aviso. For numerical reconstruction, most computer languages such as MATLAB or software languages such as ANSYS APDL can be used. For reconstructing nanomaterial, for example, the FIB-SEM technique can be used. This method uses two beams. One is focused ion beam, which slices the material, and the other one is the electron beam used to take the image from a different angle. So it is noted that this is an intrusive method and material is destroyed after the test. One major advantage of this method is its high resolution SEM. Here shows some typical steps for image processing and the final 3D solid model. Alternatively, we could reconstruct the catalyst layer structure numerically based on certain reconstruction algorithms. Here we obtain a two-point correlation from experiments of FIB-SEM, and using stochastic algorithm to reconstruct a catalyst layer structure that compares close to this correlation. Here shows a comparison of experimental images on the top with numerical generated geometry. The middle images are randomly generated, where the bottom images are generated according to a two-point correlation based on the experimental images. We can see apparently the one with similar correlation compares well with the experimental images. So here is another example of reconstructing microstructure. So this time it's a GDL for PMFC, which is carbon fibers stacked randomly layer by layer. Then we perform a finite element analysis on the solid model and obtain stress and strain distributions as shown on the right. So this is a case with not only carbon fibers, but also the binder in the GDO considered in the reconstruction. So it is found the binder affects the computer effective diversity very much. So see the comparison with experiment data with good agreement here and here. In this slide, for microstructure with compression ratio ranging from 0 to 75% were simulated. For each reconstruct microstructure, simulation results in three directions were calculated. It is noticed carbon felt is highly porous material, which is beneficial characteristic in terms of both electrolyte penetration and low liquid pressure drops through the electrodes. We have also tried the same approach with a high temperature PMFC catalyst layer, which is a mixture of carbon support catalyst and PDFE. Well, this case is special is after the PBI membrane is doped with phosphoric acid, it is combined with two TDE electrodes. So excessive phosphoric acid will be squeezed into the catalyst layers and forms the pathway for proton in the catalyst layer. So the FIB-SEM image shows the components of the layer And the center image shows the reconstructed model. Now we come to the pore-scale modeling, which involves different methods to compute effective transport properties as well as the solid mechanics of the material under external forces. So I'm going to briefly talk about these methods and show some results. So these models are pore-scale model, lattice Boltzmann model, and finite element analysis. The idea of pore-scale simulation is to solve the so-called point equations instead of the volume average microscopic equations over the microstructural geometry we just created. After solving these points equations, we compute the effective transfer property based on the fluxes obtained through the domain. So the transport equations are mainly Laplace equations such as mass diffusion, heat conduction, and electric conduction. For example, in the pore-scale model or PSM solution for catalyst layer, which has media for gas diffusion, electron, and ion conduction, we can solve the conservation equations for gas species and charged species and obtain the differentiabilities for these or conductivity. For finite element analysis, we perform explicit simulation of fiber movement subject to a compression force from the top of the material. In this case, it's a BIP carbon felt. For fibrous materials such as this carbon felt material shown here, it is interesting to note that change in an isotropy of the carbon felt under compression. Yes, there's not much difference in terms of diffusivity decrease when compression ratio is increased. But on the other hand, the through plane in the z direction is not much increase, whereas in the in-plane direction, you see a significant increase in terms of electrical conductivity at high compression ratio. Here shows a simulation of liquid water movement inside a compressed GDL. The simulation was based on a multiple relaxation time LBM code. The animation on the right shows different movement of water in the GDL. When there is a landing in the domain, water is redirected towards the opening. Note that also water flows around the spot that is highly compressed. Here's another example of LBM simulation where it shows the penetration of phosphoric acid through a high temperature PMFC catalyst layer at different times. For the case of high temperature PMFC, only the catalysts covered by phosphoric acid are active sites. On the other hand, ionic conductivity of the catalyst layer depends on the amount of phosphoric acid. Therefore, it becomes an optimization problem, and simulating the movement of phosphoric acid is helpful in providing insights into the problem. On the right, it shows the fluid viscosity would affect penetration. Finally, with the first two steps achieved, we now can incorporate the results into a CFD macroscopic platform. We now again use the PMFC case as an example, where we solve the complete set of conservation equations, including conservation of mass, momentum, species, energy, and charge species. We need effective transport properties of the materials for a model closure. And specifically, we need the diffusivities of gas species, charge species, and heat. We also need the Young's modules for solid mechanics. So this table shows how these properties are related to the governing equations and how they are coupled. And the point is also to illustrate that the stress and strain has a big impact to all these properties. So it makes a solid mechanics simulation very important. Here we show an example of macroscopic model which use effective transport properties. The left figure shows the stress distribution of metallic bipolar plates and the MEA. The figure on the right compares the prediction with or without mechanical deformation considered in the model. One can see that significant discrepancy occurring under the regions where deformation occurs most, obviously. So here is another example for a VIFB model when effective transport property are applied. One can see that distributions in the flow channel varying for different levels of compression on the carbon field shown earlier. I hope so far I have made my points clear and you have understood how mesoscopic modeling can be done and how we could enhance the validity of the macroscopic models by these mesoscopic models. That being said, I think there still exist many challenges and opportunities for future study. To make it short, here is a list, namely a hybrid modeling with CFD plus all sorts of different combination, CFD with solid mechanics, CFD with PSM, etc. And secondly, to develop operando microscopy so that you can perform in situ operando observation of nanoscale materials. And furthermore, to develop local measurements to get surface properties, diffusivities, etc. And to develop multi-scale simulation technique, which can better bridge both microscopic and the macroscopic models. And lastly, to model the microstructure change during fabrication processes. With this, I would like to conclude my talk by thanking a few organizations, collaborators, and funding agencies, as shown here. And finally, thank you all for your attention. I cordially invite you to visit us in Wuhan, China, when the COVID-19 pandemic is over. Thank you.